All right, so what we're going to start talking about in class tomorrow is the idea of momentum, and we'll end up um, talking about momentum for a system. But let's start by just talking about the sort of simplest idea, which is linear momentum for a single particle. And I can define the linear momentum in terms of a single particle through this equation. So P here is the linear momentum. It's often just what we call the momentum. And I get it by taking mass times velocity. So a couple things to consider here. One is that momentum is clearly a vector quantity, right? And so I get the x component of my momentum by taking mass times the x component of the velocity. Y component of the momentum is mass times y component of the velocity. Z component of the momentum is mass times z component of the velocity. So just like with any of our vector equations, there's really three equations buried in here, one for each component. Because mass is always a positive quantity, the second thing I see here is that the momentum vector always points in the same direction as the velocity vector. And that actually is going to be very useful because we don't have a lot of experience thinking about the momentum of a system, but we do have some experience thinking about the velocity of a system. Right? So thinking about what a particle's velocity is, its direction, whether it's changing or not, that we have some experience with. And what this equation tells us is that basically the momentum, if you can think about the velocity, then you really are thinking about the momentum, because that multiplying in the mass doesn't do anything to change its direction. The third thing that this equation is sort of indicating is that momentum is a measure of an object's quantity of motion. So one of the things that we come back to with momentum is that, again, it is such a fundamental concept, just like what we said energy was, that, again, it's hard to express clearly in words what it is that we're talking about. So the phrase that we'll often use, and this one comes straight from Newton, is that momentum is telling you about the object's quantity of motion. What does that mean? Well, again, we don't have really good words to say what that means. So instead, what we're going to do is we're going to use this equation to think about what that depends on. And so clearly what that depends on is the amount of stuff you've got, the mass, and then how fast the object is going. So you can have an incredibly large momentum by having a whole lot of stuff, or by moving very fast. And obviously, if you have a whole lot of stuff that's moving very fast, then you have an extraordinarily large momentum. Last thing is just thinking about units here. Well, the units of momentum have got to be units of mass times units of velocity. So this has got to be kilograms times meter per second. So the units of momentum are kilogram meters per second. And oddly enough, this doesn't have some other special name like a Newton or a joule or anything like that. We just always write these as kilogram meter per second. All right. So again, the idea of momentum really sort of foundationally connects to what Newton was trying to tell us. So one thing we can do now is we can come back and sort of rewrite Newton's first law so that it says objects at rest remain at rest, and objects in motion continue to move in a straight line at a constant speed, all that's the same, unless their momentum is changed by a net external force. So again, when we had talked about Newton's first law initially, we'd said that objects at rest remain at rest and objects in motion continue to move in a straight line at a constant speed unless they're acted on by a net external force. And all we're doing is really highlighting that what that net external force does is it changes an object's momentum. So if I have an unbalanced, and all an unbalanced means is that it doesn't cancel out. Right? It's not telling us that our force is crazy. It's just saying that when I take the vector sum of all the forces acting on my particle, acting on my object, acting on my system, then if they don't cancel out, that's what unbalanced means. And so if I have some non-zero external force acting on my object, then it's going to change my object's momentum. and that will show up in changing its motion. Next thing is that if the momentum is constant, the velocity is constant. And if the velocity is constant, the momentum is constant. So again, this sort of knowing one of these absolutely means that we have to know the other. And then if that's true, so if the momentum is constant, well, that means that the momentum doesn't change, and that happens when the net force is equal to 0. So if my net force, if the vector sum of my net force is 0, that means my momentum doesn't change. If my momentum doesn't change, my velocity doesn't change, which means my motion doesn't change. Similarly, we can sort of rethink Newton's second law. So again, when we said it the first time, we said the net force is equal to mass times the acceleration. But again, we know that the acceleration is really nothing more than dv dt. And all we're doing is basically taking this mass quantity and plugging it back in so that we have the momentum that we're now taking its derivative with respect to time. So this is sort of Newton's second law as Newton would have thought of it, which is that the net force acting on your system is equal to the time rate in change of the momentum. And so again, what this tells us fundamentally is that unbalanced forces act to change the momentum of a system. That's what the net external force does if it's not equal to 0. The net force and the time rate change of momentum always point in the same direction, in the same way that we said the net force and the acceleration always point in the same direction. And then graphically, we sort of understand how to read this now. This says that the net force is going to be equal to the slope, right? That we've got a derivative equation, so it's going to be the slope on a momentum versus time plot. So for the component, right, basically, so each component equation in this vector equation tells us to go look at a particular plot. The slope on that momentum component versus time plot will give you the component of the net force. So if you're interested in the x component of the net force, you're going to go look at the x component of momentum versus time, that plot, and then the slope at any instant in time will give you the x component of your object's momentum. The last thing we want to add here is we want to add in the impulse. And the impulse is basically defined to be the integral from some initial point in time to some final point in time of f dot dt. And so what the impulse is trying to measure is it's basically saying if a force acts on our object, the impulse that will be the impulse given by that force is really going to depend on what the force is, what's its magnitude, what's its direction, and then how long does it act on the object. So if I've got a variable force, fine. I just need to integrate over a variable force. If I've got a constant force, then I can pull this out, and I'm left with f dt. But either way, that's telling me what the impulse is. Now, interestingly enough, if I think about the impulse due to the net force acting on a system, so the net impulse, if you will, well, the net force is just dp dt. That's Newton's second law here. And I see that this simplifies. The dt's cancel. I change my integration, so instead of being over time, since that has disappeared, now it's over momenta. So what this tells me is the net impulse is equal to the change of momentum. So if you want to think about the impulse delivered by the net force acting on your system, well, that's going to act so that that net force will have some magnitude, it'll have some direction, it will act on your system for some amount of time, and what that's going to do is that net impulse will then change the momentum of your object. So this relationship between the net impulse and the change in momentum is known as the impulse momentum theorem. And you can see that it's actually very much like one that we've seen before, which is the work energy theorem. So the work energy theorem told us that the change in kinetic energy is equal to the net work. The impulse momentum theorem tells us that the change in momentum is equal to the net impulse. The biggest fundamental difference between these two equations, this is a scalar equation. So it's keeping track of energy, it's a scalar equation. This is a vector equation. It's keeping track of momentum and how forces change the momentum of your system. That's a vector thing. And so we just have to do what we always do with vector problems. We've got to break things up into components. We've got an equation for each relevant dimension in the problem. And so this is the, again, why this is a more complicated equation is simply because it's a vector expression. And so we'll take these ideas and talk about them first for single objects and then start talking about them for systems of objects. And then we'll end up talking about how systems of objects interact via collisions.